So let's learn about stoichiometry. What is stoichiometry, right? Stoichiometry. I promise to you it's harder to spell than it is to understand. So stoichiometry is basically a way of doing unit conversions, right? And it's the way chemists have been doing unit conversions since essentially the dawn of time, probably. It is a neat and basically perfect way to figure out how different units such as grams and liters are related, right? And you can use this in math, you can use this in physics, you can use it basically wherever. It's just it's used most often in chemistry. Okay, however, I do have to kind of note that stoichiometry only works in perfect and ideal conditions. We're assuming that we are in perfect conditions. We know that life is very imperfect, like my spelling. We do know that life is incredibly imperfect, so stoichiometry is not always going to work, but it's really helpful for like knowing how much we should be getting. So for things like theoretical yields, right? Theoretical yields. So, stoichiometry is pretty important to know. Okay, so how do we do it? How do we do stoichiometry? Well, there's a basic roadmap that you have to follow, and I'll draw that out for you. It goes like moles, and we can go to molecules, and we can go to grams, and we can go to liters, right? And so if you'll notice that we have lines that connect every single one of these guys together, and they all go to the mole, and the mole is at the heart of everything. So what is a mole, you might be asking, and what is it? Is it that little spot on your face right here, or maybe the little animal? Ooh, I don't know if I can draw a mole. This is my best attempt at drawing a star-nosed mole. Right? No. Scientists would never use something so silly like that. No, indeed. They decided to just choose a random arbitrary chemical, it's carbon 12, and say, 12 grams of carbon is 1 mole of carbon. Okay. How many molecules was that? 6.022 times 10 to the 23 molecules of that. Was it random? Yeah. But is it now officially scientific standard? Yes. So we're going to have to deal with that. Okay. So I told you that 6.022 times 10 to the 23 molecules are 1 mole. I told you that 12 grams of carbon 12 was also 1 mole. And if we look on the periodic table, we would know that carbon is element 6, maybe 7, 6. No, boron is 6. Some element number. We don't really care what element number it is. It is 6. Sorry, I just had to know for my own sake. 6. And we know that it weighs about 12.01-ish. And that carbon 12 is going to weigh 12 AMU. So what we can say is that 12 grams of carbon is going to be 1 mole of carbon. So if we had carbon 14, then we would know that 14 grams of carbon is 1 mole of carbon 14, and that's also going to be 1 mole, right? 14 AMU, 14 grams, 1. So what we know is that molar mass is a thing, and that is abbreviated oftentimes as MR. And molar mass is basically just the AMU number. So like say for sodium is going to be element 11 with like about 23 AMU. What we know then is that 23 grams is 1 mole of sodium. And then for liters, it's 22.4, right? And this one you just kind of have to memorize. Okay, so we have this roadmap, and we know that we have to follow these general guidelines. But can we go from grams immediately to liters? No, we have to follow these lines right here, and we have to go from grams to moles to liters. Okay, so far pretty easy, right? But what if we're going from multiple chemicals, right? So what if I'm saying I want chemical A to chemical B, right? Then this slightly falls apart, and there's only one really major difference that you do have to consider, and that's the fact that we can mirror this guy like this, right? And it looks super simple, but to go from moles to moles, we can't just go assume a 1-to-1 ratio. We have to use the balanced chemical equation. So say we have A plus 2x becomes 3b plus y. And these are just random chemicals, of course, just base chemicals. Then we would know that to go from 1 mole of chemical A, it takes 3 moles of chemical B. Or to make 3 moles of chemical A or B, it makes 1 mole of chemical A. Or it takes 1 mole of chemical A. Right? So this is super intuitive. This makes sense. So basically, we can maintain these same things, but the only difference is if we're hopping this bridge right in the middle. Oops, sorry, let me use a color because everyone loves color. When we're hopping that bridge, we have to remember to consult the balanced equation. Consult the balanced equation. Okay, so far so good. So far so understandable. Let's do some practice, because practice makes perfect. Life and stoichiometry may not be perfect, but practice, maybe if we practice life, we could be perfect. Okay, so let's do a really simple one. Say we had 48 grams of oxygen. How many moles of oxygen do we have? Now, if we consult the periodic table, we know that just oxygen is element 8 with 16 grams, or 16 AMU. Therefore, we know that the molar mass of O2 is 16 grams of O. So, since we have 2 oxygens, we're going to have to double it for 32 grams O2. So this is our molar mass right here. Now let's figure out how to do it. So in order to do any sort of conversions, we have to make a picket fence. Or you can be boring and do ratios or fractions, but I'd love to live the American dream, and so I want a white picket fence house, so I'm manifesting. So we're gonna put what we know right up here. It's always gonna be what we know, what's given in the problem. 48 grams of O2. And then we're gonna take this stuff right down here and this unit, and we're gonna put it right in this box. So grams of O2. And on top we're gonna put what we want. What do we want? Moles of O2. And then if we consult that that roadmap again, we have that 1 mole of O2 is the molar mass of O2 in grams, right? So then we're gonna have 32 grams of O2 is 1 mole of O2. Then we do that math, 48 over 32, that's going to be equal to, if my math is correct, 4/3 of, sorry, I'm totally blanking, 4/3. That sounds right. Wait, can I do math? 8. I'm going to use a calculator. 48 over 32. 1.5. Sorry. I meant 3/2. I can do math. I'm going to cut this out later. Okay. So let's figure out our next example then. Okay. I may not have proven myself to be a great mathematician, but I mean, I'm an okay chemist, maybe. Okay, let's figure out the next example. So say we reacted 200 grams of oxygen with an excess amount of, not oxygen, sodium hydroxide. That would be really weird to react oxygen. Sodium hydroxide with an excess amount. Maybe I am not that great of an academic. Excess. Whew, can spell. Excess amount of sulfuric acid, amount of H2SO4. How many grams? How many grams of sodium sulfate? How many grams of sodium sulfate will we make? Will be produced. Well, how many chemicals are we using? It looks like we have 3 chemicals, but really we're only going between 2 chemicals. And this is our start condition, and this is our end condition. Okay, so this is going to use that weird Frankenstein kind of roadmap, right? Where we go moles to moles, connected by moles to moles, and we're going to go grams, liters, and molex, right? And let's kind of trace out how we're going to go. Okay, well, we're starting with grams of chemical 1. Then we're going to have to, in between, or end up at grams of chemical 2. In between, we're going to have to go to moles, and then go to grams. Okay. Now we have a base plan kind of set up. But how do we hop that bridge? We have to use a balanced chemical equation, right? So we're gonna have a balanced chemical equation made. We know that NaOH reacts with H2SO4 to create H2O, because it's an acid-base equation, and Na2SO4. And then we're going to balance this equation, and with the fully balanced equation, we can now figure out how to set up our picket fence, right? I'm going to do a picket fence as usual because I really am trying to reach my American dream of knowing how to do basic math and spelling. So we're going to start with what we know, 200 grams of sodium hydroxide. Right, we bring down that given unit. We're going to go to moles because we have to get to moles. We're going to go to moles of that same chemical. And then we're going to go jump the bridge. Moles NaOH on bottom because that's what we have on top. Moles H2SO4 because that's what we have. That's what we want to get to. And ultimately, we're going to bring this guy back down one more time. H2SO4. And put grams H2SO4. Now let's fill in our values. Well, when we have moles of the same chemical, right, like we have right here and right here, we know that moles are going to be 1 and grams are going to be the molar mass. So when we think about sodium, it's going to be 23 plus 16 plus about 1, which is going to be about 40. Right? And these are rough estimates. This is not going to be perfect. And H2SO4 is going to be 2 H's, 64 oxygens, and something like 32 sulfurs. Sorry, but my mind blinked. Oh, I am so sorry about that. We are not trying to get to H2SO4. We're trying to get to Na2SO4. Reading the problem is very important. Na2SO4. Na2SO. Okay, my handwriting is suffering, but you get the idea. It's gonna be Na2SO4. I apologize for the terrible penmanship. So Na2SO4 is gonna be then 46 plus 32 plus 64. It's gonna be 110 plus 32 is about 142 grams, right? And then we notice that we have differing chemicals right here, so we have to consult our balanced chemical equation, and we know that for every 2 moles of NaOH used up, we make 1 mole of Na2SO4. Now let's do all that math, right? You're going to get rid of a 0 here, a 0 here. You're going to multiply everything on top. What color should I use? Blue. We'll multiply everything on top and divide by everything on the bottom. So Na2SO4, we're going to get rid of a 0, get rid of a 0, get rid of a 10, become 10 times 142 over 4. Right? That makes sense. Then we're going to go divide something like 71 times 355 grams of sodium sulfate. Okay, and there you have it. That's everything you need to know for stoichiometry. Good luck, and yeah.